Welcome to another podcast. In this episode, we're going to be looking at calculating z-scores. Z-scores are one of the more important things we look at during the statistics unit because they give us a frame of reference for comparing values across multiple scales. That's why z-scores are often called a measure of relative standing. Let's start off by just looking at the formula. If you're trying to calculate a z-score, then the z-score corresponding to a data point x is generally x minus mu over sigma. Now remember, mu is the population mean, and sigma is the population standard deviation. Oftentimes we don't have those values. If we did, that would make statistics a lot easier. So a bunch of statistics revolves around sampling and looking at sample statistics. In this case, we replace mu with x bar and sigma with what we've been calling sx, or you could just do sd for short. So it's the exact same symbols in the exact same places. It's just sample statistics versus population statistics. Let's just do a couple of examples to get a feel for it. As we do these examples, I want to show not only what we're calculating, but I want us to also interpret it as we go through. So let's suppose that we're working on a problem where we're given that the population mean is 100 and the population standard deviation is 10. And I ask you to find the z-score that corresponds to a data point of 20. So where does the data point 20 fall on that scale? Well, one of the things I want to do is come over here and actually draw out this distribution. And we've done this enough in class, you should be a pro at this by now. But we've got our bell curve. The center of the distribution is at 100. And we're going to count by tens because that's what our standard deviation is. Now typically we do not want to go more than 3 standard deviations either above or below the mean. And so I'll stop it at 70 here on the low side and 130 on the high side. Just keep in mind though that technically this curve extends in both directions actually infinitely. Although practically for some data sets they may only be positive values or something like that. But the data set extends in both directions. So for a z-score corresponding to the data point 20, we're just simply going to apply the formula up here. The data point is 20, the mean is 100, and the standard deviation is 10. Plugging those in, we get minus 8. So the question is, what does the number minus 8 mean? Well, minus 8 refers to 8 standard deviations below the mean. So this is 8 deviations below the mean. So let's sort of put this into context. Between plus and minus 3 standard deviations is 95% of the data. So the picture we're looking at is roughly 95% of all possible data. To have a standard deviation or to have a z-score of -8 means you're so far on the low side that you're not even, in probability terms, it's not very likely that you would ever see such a data point on this distribution. Think of it this way, maybe these are pulse rates, for example. 130 is kind of high for a pulse rate, but if these were pulse rates that we were looking at, a value of 20 for a pulse, well, that's so low that the person's likely to be dead. And so if you're actually sampling living people and their pulse rates, a data value of 20 would not be a data value that you would expect to occur. Let's try another one right quick. Let's try one that's a little bit more realistic. How about a z-score corresponding to the data point 89.2? So using the formula here, we get negative 1.08. Alright, so this is good. On our graph, 89.2 is approximately here. And it corresponds to a z-score of negative 1.08. Now here's the reason for that. All we've done is we've calculated that this distance here is 1.0 standard deviations below the mean. So if you count by standard deviations or count by your tick marks, it's a little bit past the first tick mark below the mean, which is exactly where we find 89.2. So let's try one more. Let's find the z-score that corresponds to a data value of 125. So just keep in mind here that these negatives meant below the mean in both cases. So for this one, clearly the number 125 is larger than the mean of 100. And so we should get a positive number here. And if we calculate this z-score, we get 2.5. So this suggests that the point 125 is 2.5 standard deviations above the mean. And that's exactly where it is. It's halfway between the second and the third tick mark, so it's 2.5 standard deviations above the mean. So just always keep in mind that all we're doing with z-scores is we're sort of plotting or telling the distance from the mean to the data point, but not in terms of the data points, in terms of the standard deviation of the set. So we're counting by standard deviations. Let's try another question that's slightly different. What value is 2.3 standard deviations below the mean? So as I read that, 2.3 standard deviations below the mean would correspond to some data point x that has a z-score of negative 2.3. So I can sort of work this problem in reverse. If I set negative 2.3 equal to the data point I'm looking to solve for, then I can just do some simple algebra at this point. And I ended up switching a negative to a positive here. Let me correct that. And let's see here, 100 minus 23, we get 77. So the data point x is 77 in this case. So the z-score for 77 is negative 2.3. So does that make sense? Well, if you look at the data set, this would say that the data point 77 is more than 2 tick marks away. So 1, 2 is a little bit more. Is this where about 77 is? Sure. So that makes a lot of sense. So please keep in mind that even though I've given you this z-score formula, it can be used in a couple different ways. You can either solve for the z-score, or you can be asked to solve for the data point, reversing it the way that I've done here. Alright, I hope this gave you a little bit more insight into how to calculate z-scores as well as what the z-score means in terms of the data set. That's the bigger idea, is what are these z-scores that are calculating, what do they mean in terms of the data set? Because we're going to be using them to compare different data sets coming up, and it'll be a lot easier for you if you have sort of a concept or a picture in your head of what the z-score is that we're actually calculating.